that I did not get that videoed. But so what we were talking about, even before we can understand what's been oxidized or reduced, we have to understand what their oxidation numbers are. We did a couple of examples on slide 7, so I've got 8 and 9 up here today. And we'll do a couple of examples including carbon. And if you remember, the way that I do oxidation numbers is on a line underneath. I do my oxidation numbers, that's what ON stands for, and then if I need any work, I do it down below. For example, and then I split each of my elements up, and then I come back to my guidelines. There's really only 2 elements per se that are in compounds that we have guidelines about. Those are hydrogen is +1, oxygen is -2. I have a hydrogen right here. Each hydrogen is +1. I have 4 of them, so I'm going to write +4 down here, 4 or +4. And again, this is just my work, or really where I'm keeping track of my math. And what I said was that because there's no charge on CH4, that's methane by the way, then I know that the oxidation numbers have to add up to 0. Since there's only 1 carbon, that whole carbon has that 1 carbon has an oxidation number of -4. And that's my process for doing that. And one of the things that becomes much more apparent when you get to organic chemistry is that the oxidation states of carbon are really important. Carbon goes from -4 in that example, depending upon the number of hydrogens and oxygens, all the way over to carbon dioxide. For carbon dioxide, we said in compounds, oxygen is -2. There are 2 of them. That multiplies out to -4. I have 1 carbon and no charge on this molecule. And so the oxidation number for carbon is +4. And carbon on the intermediate ones is between -4 and +4. Another thing we said last time was that oxidation numbers are hypothetical charges. And so a -4 or a +4 helps us keep track of the electron movement, as we'll see. But really the biggest charges we ever see that are true charges are +3 and -3. So they're hypothetical, and we'll use them shortly. Now I want to do this example. This is propane C3h8. I always gang up all my carbons and hydrogens together, no matter how I give it to you, or how you give it to me. This is a nice example because it has multiple carbons, so we get to see how to handle that. It has multiple hydrogens. Each hydrogen still +1. There are 8 of them, so that's +8. There's no charge again on this species, so the sum of the oxidation numbers has to equal 0. And for this one, I'm definitely going to do it because I know that my carbons have to total -8. And there are 3 of them. And at least as far as we do oxidation numbers so far, we assume that all the carbons are the same and share the same charge. And if you get a fractional number, that's fine. I'm going to get -8/3 for that. And again, I'll remind you, these are hypothetical charges that allow us to keep track of electrons, and even non-whole numbers are fine. Any questions about what I've got up on the board so far? Okay. All right, and if you put 2.67 there, that's fine as well. Fractions or decimals are fine. Now let's do our first redox reaction. In this problem statement, it says, in a redox reaction, determine the oxidation number for each element, and then determine what, if anything, has been oxidized or reduced. I give you these reactions. Again, remember that you're on your exam, they're single concept problems except for the last problem. So there are two different things that I can ask you. I can ask you to write, say, a combustion reaction. That could be one problem. Not that this is. Or I could ask you to do oxidation numbers, in which case I would have to give you the balanced reaction. In these balanced reactions, what I like to do in Chem 400 is ignore coefficients. There are ways to do it that you can include them, but that's the way I do it. But otherwise, I'm going to write oxidation number right here. I'm going to do the same sort of setup I've done before. Where each element will have its own oxidation number, but I will not consider coefficients. So I'm only looking at the formulas, and so really what I'm doing is the same thing I'm doing over here, except multiple times in the same time. What I like to do then is I like to go through and hit my oxygens, and anytime oxygen is in a compound that's -2, so I'll put a -2 here, I'll put a -2 here for this oxygen. -2's all around. -2 for you, -2 for you. Everyone that's oxygen gets -2. And then I like to do my hydrogens. I have a +1 right there. And way over here on the other side, I get a +1. Water's sort of my internal calibration, because if I remember that hydrogen's +1 and there are 2 of them, 1 oxygen, no charge on the molecule, water does itself. So that's sort of a way to check in and see what's going on. From there, let's see. Here we have an element all by itself, what's called an element-only formula. For element-only formulas, what's the oxidation number? 0, goose egg, donut. And so you don't have to have anything down here. You actually never do, but just when it helps you, put stuff down. Here for nitric acid, there's one element that I don't know. I do have to consider that there are 3 oxygens. 3 times -2 is -6. I like to bring down my +1 for my hydrogen. No charge, actually no charge on any of these species, but so no charge, so the whole thing has to add up to 0. And now, nitrogen, I have 1 of them, and what will the oxidation be on that nitrogen? +5. It'll be +5. Some people like to put 1 + x - 6 = 0 and solve for the x. The thing that you want to be careful about, and that over my, wow, I'm old, 20 years of experience teaching, is that in this kind of simple math, it's easy to think, and your brain tricks you into thinking it's -5. So make sure, like, I like to put +5 there, and then I like to go back and look at the numbers and see that they add up. So, because another thing about Chemistry 400, it's really lovely when problems such as this are sort of self-checking. You can see if it's done right. Any questions about that? All right, well, here. Copper nitrate. At first glance, it looks like there are 2 elements that we don't know. There's one rule that we have to remember, one guideline, and that is monoatomic ions have their charge equals oxidation number. And in this particular case, we know that's Cu2+, because we know an ionic compound when we see one, and in the end, this is copper ions and nitrate ions. And that's where your nomenclature is going to help you yet again, if you can separate those into the ions that you know. I guess maybe not nomenclature, but knowing what your ions are and what their charges are. Okay. It's copper 2+. That means its oxidation number is 2 plus 2. And again, I don't care. Copper 2+ is for ions how you typically put the charge, but if you put +2, that's fine. The numbers here for oxidation numbers are typically the plus first, but again, that part doesn't worry me. I'll always mark them right, even if you just put 2 there, because I'll assume it's plus 2. Okay, now comes the heavy math. I have 6 oxygens total. Because I count subscripts, I don't count coefficients. 6 oxygens times minus 2 is minus 12. I have 1 copper ion. The whole thing equals 0. And now I get plus 10 here. But inside this compound, how many nitrogens are there? 2. 10 divided by 2 is 5 plus 5. And a hint about this, really this is the NO3, this is pretty much the nitrate ion, and it's got plus 5. And this is the nitrate ion, and it's plus 5, and so those will be the same. Continuing onwards, we get nitrogen is plus 4. Any questions about any of those examples on how to do oxidation numbers? If not, then we have to think about what was oxidized and what was reduced. The thing that was oxidized lost electrons. And I guess even before I do oxidation and reduction, I like to see if anything's changed oxidation number. Here I have a 0 for copper and a plus 2. So that's going to be one of the things that changes. What other element changes? Nitrogen changes from plus 5 there we go, plus 4. Now, as we go from 0 to plus 2, the oxidation number is getting more positive. More positive means that copper must have lost electrons. And we can show that, so the reactant that was oxidized was copper. And we might say copper went from copper to copper 2 plus. Plus 2 electrons. And we said that in oxidation half reactions, electrons would be a product. When you gain electrons, you're going to become either closer to negative or more negative as we move from plus 5 to plus 4. Nitrogen in this case, and let's say this, I'm not going to do this for the nitrogen. It's a little more complicated than that. But what I do want you to know is that nitrogen in nitric acid was reduced. It does go from plus 5 to plus 4, but since it's in a covalent compound, I will say it's a little more complicated. Now, I don't ask this question, but you should know about it. What are the oxidizing agents and what are the reducing agents? And you can see it on the homework, so you should do it. However, I'm going to put a parenthesis around it because you will not see them on the exam. The thing that is the oxidizing agent was itself reduced. Oxidizing agent was reduced. And allowed oxidation to occur. And so the oxidizing agent, well, typically you actually do say the whole compound for that. And so the oxidizing agent was nitric acid. Although really it was nitrogen that was reduced. Reducing agent was the thing that was oxidized. So we can say, was oxidized, allowed. Allowed reduction to occur, and in this case, it's common. So, and if you look over old exams, you'll typically see one of these types of problems on them, or some version of oxidation and reduction numbers on them, for sure. Questions about this problem? Then let's keep going. Some of these are going to end up being companion problems. This one's going to end up being a companion problem. Companion problems have their answers on the Chem 400 website, printed out in PDF form. Let's keep going and do the next one. This one is a single replacement reaction. We've talked about double replacement before. Those of you who took Chem 300 will know single replacement reactions as well. We will cover single replacement reactions in lab next week. Single replacement reactions are not one of our reaction types. If it's one of our reaction types, I can ask you to write it on an exam. I will not ask you to write this on an exam. But I very much could ask you to do the oxidation numbers for these. They're not too bad. Here we have an element by itself. Oxidation number, please. 0. We have another element by itself. Also 0. From there, I have hydrogens and oxygens. +1 for hydrogen, -2 for oxygen, -2 for oxygen. Filling in for the sulfate ion, I have 2 hydrogens, I have 4 oxygens. What is the oxidation number on that sulfate? 6. +6. And oftentimes, once I've been doing this for a little bit, I'll skip putting the +6 down here and just put it up there. And at this point, I will emphasize that it is the oxidation numbers that I grade. Partial credit, I guess, could be done for if you mess up the oxidation numbers for the work done there. But it is, and so on an exam, make it clear what your final answer is. Here I've got magnesium sulfate. Magnesium is a 2+ monatomic ion. I have 4 oxygens again, and I have +6 for sulfur. The sulfur is not being oxidized or reduced. Magnesium is definitely changing oxidation number. Hydrogen, also changing oxidation number. These blue lines and the circles are all part of my sort of process. You don't have to have them, but it helps me stay organized about it. Magnesium, was magnesium oxidized or reduced? It was oxidized, it became more positive. Leo. The other one better be grrr. Then it is, because +1 to 0 is becoming more negative or closer to negative. It is true as well that as we go from 0 to +2, there are 2 electrons being lost, and those will show up in our oxidation half reaction. These magnesium ions are aqueous. And I will ask you to put phases in here, especially since I give you the phases up here. Now, if this was a total ionic equation and you saw H2SO4, you would say strong acid, also strong electrolyte, breaks up 100% into ions, and here's what we will do. You end up with 2 H pluses plus 2 electrons. Go to hydrogen gas. And we'll do this in lab for lab number 3 as well. We'll actually do the reactions, like literally do them. And then we will literally write everything that you've done just here for each of them. Okay. Any questions about this? So number 12, very similar, also a companion problem. Combustion reactions are redox reactions. Let's go over this one, and I guess I'll keep this one up here this time. So 13. Well, let's see. Let's see. Yeah, we knew that was going. I knew that was going to happen. Let's see if it starts back up again. Fortunately, I know where we were. Where were we? We were doing this reaction. Redox. This is a redox reaction. Yeah, it could take a couple minutes, but it should warm up. This is a redox reaction. We're going to do oxidation numbers for it. There we go. We can almost see it, can't we? Well, let me do it actually using the board then.
Talking about individual atoms and not 2 hydrogens and H2O, but each one.
We were talking about each one. Each atom has an oxidation number. Yes. That is definitely one of the take-home messages. All right, we're back in business. Here we have, and what I'll do is, I like to just cross them out, because otherwise they're distracting to me. But cross out your coefficients, go ahead and, for all the hydrogens, what will the oxidation number be? In compounds, hydrogens are +1. In compounds, oxygens are each -2, and oxygen by itself is just 0. Then there's only one thing left for each compound, at least. We've worked propane before, but let's work it again. We have 8 hydrogens, that's +8. The charge on the compound is 0. We have -8 right here. For 3 different carbons, each one is 1/3 of 8, or 8/3. Sorry, -8/3. Let me make sure that's On the other side, we have carbon dioxide. 2 oxygens. That carbon must be +4. And lo and behold. Same process, circle anything that changes. In this case, oxygen changes. Was oxygen oxidized or reduced? It was reduced. And hopefully carbon was oxidized, and sure it was. And perhaps we get back to the original meaning of oxidized, which is add it to oxygen and you will be oxidized. Lo and behold, it is oxidized, the carbon.
So you have 2 oxygens in the product.
Yes, I have. Oh, yeah. I connected to this one. I could have connected to either or both. At least one, though. I mean, it's just connect them to at least one. I guess what I'm looking for here is for you to identify the things that change. So, and as long as you identify one of them, I'm happy. But you could do both, and that'd be fine.
They're
too.
identical. Is that typical?
They're identical. Is that typical? Certainly for combustion reactions.
No, I mean CO2, oxygen and CO2, and oxygen and H2O.
Oxygen in any compound is -2.
Right.
And the only time it's different is when it's oxygen by itself. O2 is oxidation number 0. Yeah. Any other questions? Jason?
How would we list it if a compound split into 2 different moles, or the carbon split into 2 different compounds, that one was oxidized and one was reduced?
Good question. So what that gets, so if you had, say, carbon that was 0, which is an option, you can't have oxidation number 0. They're just hypothetical charges, and 0 is fine. And you had carbon that was -2 and carbon that was +2. I don't know if that would, in particular, would ever happen, but other elements do this. And you would connect them, say one was oxidized, one was reduced. That's possible. It's not common, but it is possible. Yeah. Does that answer your question?
Yeah.
Yeah. That's the key, is you're looking for what changes, and it can be the same thing that changes both ways. Yeah. Any other questions? That's why I like this process of circling things and then connecting them. It's sort of, for me, it makes sense, but you don't have to do it. All right.
Sorry if it's a stupid question. What is the potential significance or use of this concept?
Excuse me. Why do we care if things were oxidized and reduced? Is that sort of the heart of your question? So,
It's probably a big answer.
right. I would try and give you a decent short answer for this. One, so oxidation reduction reactions, when something's oxidized or reduced, it oftentimes means the reaction will occur. And so while we're not at the state yet to say when reactions occur or not, that's part of it. When you get to chemistry 401, and even if you're not, it's a good thing to know, but for 401, we're going to start here. We're going to say you already know how to balance redox reactions. And the movement of electrons, so when you use a battery is a redox reaction that makes the electrons from the reduction process go to the oxidation process through a wire. And so batteries are pretty ubiquitous these days. This is the beginning of that process as well. So And it's just, as we start thinking about in biology, so these are the compounds, so almost all biological reactions are redox reactions. So as you take, I mean, I'm going off script here. All right, I'm going to erase this. Glucose plus oxygen goes to carbon dioxide and H2O. I think that's balanced. That's a redox reaction right there. And what makes it so beautiful in biology is that this reaction, this is the overall process, but it takes like 12 steps to occur. And each of those steps harness the electrons to help us live. I mean, that's the extremely short version of how this relates to it.
They steal electrons from somewhere.
Right. So as things give up reactions, I think there's like, so there's ATP and ADP involved, NADH, NADH plus, or something like that. Anyway, I know it's biology, right? So interesting, not in my wheelhouse. And Alicia, what I will say is, always ask, why are we doing things, right? Yeah, no, so like, because it's always useful to know, and if you it's so hard to do things when you don't know why you're doing it, right? And I know everybody in here, I asked you, why are you taking Chemistry 400? Biggest answer I got, because somebody else told me I have to do what I want to do. So, and that's fair enough. Nobody takes this class for fun. Why are you in 400? Not for fun, you know, I didn't have anything to do on my Mondays and Wednesdays. They're driven to get someplace. And I know there are some chemistry majors, but most are not. Anyway, if you're ever feeling, especially if you're feeling like, why am I here? Check in, right? See the importance of these things. Anyway, that's a touch on it, but there are reasons, and know that I am thinking about it. Okay, now next topic is going to be a chemistry, don't get topic whiplash, because it is quite a change. But there's some cleanup items that we have to do. One is for very small concentrations, and these are going to be two main sets of units, parts per million and parts per billion. If you ask me why we're doing this, it's because these are the levels of concentrations of pollutants in our atmosphere and pollutants in our water, and good things in our water as well. So electrolytes, well water, water that comes into your house. They are based on the density of water. After lab number 1, and when we do calculations, we will assume 1.00 gram per milliliter for the density of water. We will assume 1.00 grams per milliliter for the density of water. We now know, and we knew this before, that it's very close to that number. But now we will assume it, and that'll be underlying these calculations. All right. Now, parts per million, parts per billion, you'll note that the definitions of parts per million and parts per billion are on your conversion and equation sheet, so you have them. However, I'm going to give you my version of it. Parts per million and parts per billion will always refer to very small concentrations of solutes. In this case, the solute could be calcium ions. That is the solute on homework number 3 on the problem that you're working with. It's equal to 1 times 10 to the minus 6 grams of calcium 2 plus per milliliter of solution. And sometimes, because the concentrations of the solutes are so low, we sort of ignore the fact that it is a solution, and we sometimes just call this milliliters of water. Water has always got something dissolved in it. It is always a solution of some sort, whether we pay attention to that factor or not. Anyway, this for me is the definition of a part per million. There are other ways of looking at it. Another way of looking at it would be if you had 1 milligram of calcium ion in 1 liter of solution. This is the same definition with the units changed. If you take milligrams and turn them into grams, liters, turn them into milliliters, you get this 1 times 10 to the minus 6. But what will happen is you'll be reading a journal or a New York Times article, and they'll list parts per million like this. Parts per billion. One part per billion lead. Well, parts per million is 10 to the minus 6. Parts per billion is going to be 10 to the minus 9.
Is that safe to drink?
1 part per billion lead. Is that safe to drink? I believe that the standard is 15 parts per billion for lead, and so yes, it should be. I have to check in with that. Sometimes there are so many numbers dancing in my head that I mix them up. But I know, of course, it's very low, and of course, if you were in Flint, Michigan, or lately now there's an issue in Newark, New Jersey, where there's spikes in the amount of lead that's in there. It does affect brain activity, especially in young children. There was also a recent report. You heard that the Notre Dame Cathedral caught fire? They tested the air for lead from the lead-based parts of the cathedral and found big spikes downwind from the cathedral during the fire. So that, I mean, and it wasn't even parts per billion. It might have been parts per million then. And that's, I mean, that's. We can measure it. They're actually getting down to parts per trillion now for some chemical tests. Right, so to answer your question very long-windedly, yes, 1 part per billion is of lead is considered safe. Considered safe, and I would say it is. Yeah. Now. Those are the definitions. How do we use them? Problem, what is the concentration in parts per... Oh. We're going to leave these as companion problems. We're going to actually do the next ones. There it is. I knew it. The action level concentration for lead in drinking water is 15 parts per billion. The recommended amount of fluid consumption per day is 2.0 liters. How many atoms of lead are in 2.0 liters of water with a concentration of 15 parts per billion lead? Okay, so if we skipped the ones on the previous page, which were plug and chug, like one-step problems, I think it's very worthwhile to do them. This is a more complicated example, and this is the level to be test ready that you want to be. And this problem is very tough as we're introducing it, but hopefully as we work through it, it'll make sense. First thing we're going to do is we're going to take 15 parts per billion lead, and we're going to turn it into something like this, because we're used to grams and we're used to milliliters. We're not used to this thing called parts per billion yet. And this is one of the reasons I give you these definitions on your conversion equation sheet. And I don't know if I've mentioned this yet, but you will have your conversion equation sheet on the exams. For example, on exam 1, attached to your exam will be the periodic table and the full page of conversions, the first page, because that's all we've gotten to yet. And on the bottom are the definitions of parts per million and parts parts per million's on there. I should say this, you may have to remember parts per billion. But if you remember parts per million, I don't know, I have to check that. Anyway, you will have this stuff. And what I suggest is that as you do your homework, use that periodic table and that conversion and equation sheet so you're used to where everything is. So you're used to knowing if Avogadro's number is on there or if you have to remember it. Is it on there? I don't know, but it'd be useful to know before the first exam. Can't decide whether I'm scaring you or reassuring you each time I mention that. Like, first exam. Anyway, hopefully it's reassuring. All right, so 15 parts per billion. 1 part per billion is this. 15 parts per billion will be 15 times 10 to the minus 9 grams per milliliter. This is lead, good. 15, so I just took the 1s and replaced them by 15s in that definition. It's a little weird because 15 times 10 to the 9 is really 1.5 times 10 to the minus 8. But that's still the case. And I just put it, should convert it into better scientific notation, and then put the whole thing over milliliters of solution. Because parts per million and parts per billion are conversion factors. They're units of concentration, and units of concentration, moles per liter molarity, allows you to take a volume of solution and turn it into a number of moles. This one will allow us to take a volume of solution and turn it into grams. And so it is also a concentration similar. In this particular problem, it says the recommended amount of fluid consumption is 2 liters per day. I am going to convert that directly to milliliters. It is 2,000 milliliters. And then I will use my parts per billion right here as my conversion factor so that my milliliters cancel. And I don't know, I like to put 1s whenever I do my unit conversion factors. You don't have to, but I just thought I'd sneak that one in. My milliliters cancel, now I have grams. Where am I going on this problem? Well, that was a rhetorical question. I'm asking about atoms. So my next steps are going to be to convert grams into moles. Moles using Avogadro's number. Wow, it would be really useful to know if Avogadro's number was on that conversion equation sheet. Because if it is, you don't have to remember it. Maybe you know it already. If it isn't, it does come up. I look at my periodic table. I've got one right here. I'm going to use 207.2. Grams of lead per mole of lead, and then 1 mole of anything, but in particular lead, is 6.022 times 10 to the 23rd atoms. And do this in multiple steps however you want. I've strung them all together right now. And what I get is 8.7 times 10 to the 16 atoms of lead as the daily amount that you can consume and still be considered safe. which is a lot, but still way less than a mole. So parts per million and parts per billion are units of concentrations that are used for very dilute solutions because they're very small concentrations. And yet they're totally measurable and totally important in our lives. Any questions on this? Yeah.
Yeah, how do they measure that? What kind of machines do they use?
Great question. So the instrument that they use, I say great question because I sort of know the answer to this one. So they use what's called an atomic absorption spectrometer. And they will take a solution that has this concentration, 15 parts per billion lead, and they actually run the solution. They actually burn it. The burning takes anything that's lead 2 plus or lead that's any charge and actually turns it into lead metal, and then it vaporizes it. That's how hot it is. And it turns out that lead metal, as long as you know what kind of lead, you can then pass a laser through it. That laser tells you by how many photons are absorbed, how many lead atoms you have. Anyway, there's more to it than that, but and for lead, I believe they can pretty straightforwardly do parts per trillion now, because it's such a metal of interest. And like we can talk more about it if you want, but that's, so chemists are, when you think about chemistry and chemistry testing, did you hear about the Triple Crown winner? Or was it Justified or something like that? Failed a drug test, but the racing board in California said, we don't care, we still want them to win the Triple Crown. That just came out in horse racing. Anyway, and so how did they test that? They tested for a certain type of drug. So chemical testing, huge industry. Did you hear about Volkswagen and how their diesels were cheaters? That they had a computer inside that could tell when they were on the emissions testing kit, and they would ramp down the emissions. So my wife had one of those that got recalled. She got all the money she paid for it and pain and suffering money back for it after 3 years of having the car. And still she was sad on one level because the cars really worked well, but they cheated. But that was Cal EPA who caught them by testing parts per million, parts per billion of emissions. A huge industry, huge testing. Doping, with the baseball players when they were using steroids. How do they figure that stuff out? They test it.
Is it true that the laws governing the tap water in California are stricter than bottled water?
I would have to check on that, but I know we have any tap water that you get. And so I'm on a well, so I'm responsible for the safety of my own water. But any agency, they are very strict. I imagine that's true, but I don't know.
Maybe it depends on the municipality.
The one thing I'll say is, since they turn all the bottled water they get from tap water, they start with pretty good water. Anyway, so much chemistry out there. Now I'm getting excited. All right, so that's parts per million, parts per billion. This one is a companion problem for polychlorinated biphenyls, PCBs. PCBs are used in wiring to make wiring for basically anything, flame retardant. All right, now it's time for acids, bases, and pH. For those of you who had discussion this morning, you will have seen some of the problem solving for this. Many people come into Chem 400 knowing a lot about or something about acids and bases. As always, from now till the end of class, we cover everything super thoroughly, at least in my mind. And that means we start with acids and bases. And a definition of an acid. a substance that yields in excess of hydrogen ions. Those are H+, hydrogen ions when dissolved in water. We have some examples here. Hydrochloric acid. HCl, strong or weak acid?
Strong.
Strong acid. We know that HCl goes 100% when it and splits into ions. Now, H2SO4, strong or weak acid? Strong acid. H2SO4 is also what's called a diprotic acid. Di meaning two, protic meaning protons, which are really just H+. When you write these reactions, you always do one proton at a time, or one H+ per reaction, per RXN. Let me show you what that looks like. The first reaction has one H+, plus hydrogen sulfate, or bisulfate if you will. Now let me ask you this, HSO4 minus, strong or weak acid? It is weak. It has to be because it's not one of our 7 strong acids, and yet it's got an H in the front. Strong acid, weak acid. Oh, and there it is, good. Oh, so let me do this 100%, because that's what we get for strong acids. HSO4 minus, weak acid, and for weak acids, they break down into ions less than 5%. So they still break into ions. But less than 5%. And this is a slightly different way of writing it than we did when we talked about weak electrolytes, but it means the same thing. We could also say that this, in this reaction, has greater than 95% and less than 5% of each of those. That's another way of saying the same thing. And I'll just to emphasize, hydrogen sulfate is a weak acid. And that's why it's important to know your 7 strong acids. Acetic acid, also a weak acid, thank you. Does break into some ions, like hydrogen sulfate, less than 5%. Does make H+. The H+ here is the H at the end. And so we are left with CH3COO minus. And all of these are acids that fit this definition because they're all making an excess or some hydrogen ions. Different amounts, it's true. Not all hydrogens are acidic. Meaning are acids. If we were to draw the Lewis structure right here, I know we haven't done Lewis structures yet, but I'm still going to draw a couple of them. There's the H. We can draw another one over here. this time for sulfuric acid, and I've laid out all the atoms. I still have a couple more things to do. There's the full Lewis structure. Let me do one more. This time we're going to do acetic acid. I've drawn acetic acids before, but let's do it again. Seems like every lecture I talk about this COH group, and today is no exception. Each of my oxygens has 2 pairs of electrons. Now when I say acidic hydrogens, what I mean is make H+. Some amount of H+. Just like here, an acid yields H+. Could be a lot, could be a small percent. Now I'm going to circle them. So there's only one H here. That's got to be the one that forms H+. Only 2 H's here. But there's 4 H's down here, and I'm drawing distinction now between the H bonded to the O and the H is bonded to the C. The H is bonded to the C never make H+. That is a general, right? In Chemistry 400, we want you to know the things that are true 90+% of the time, and that one's true 100% of the time in Chem 400. So let me go to red for a second. Not. Is that still a thing? Not H+. Okay. Does make H+. Blue ones. Okay.
We haven't talked about H bond. Does it have something to do with that? Or?
Does it have anything to do with H bonds?
Probably not.
Well, the short answer is no.
It's intermolecular first.
Right. The slightly longer answer is this HO bond we know as partial positive and partial negative. And that is like, so it's the same bond that we're concerned with, but different properties, right? This is, when we make H+, we break a covalent bond. That's going to be making H+. When we talk about intermolecular forces, that bond will still be intact. So we're getting there.
I'm talking
Yes.
about the CH.
Oh, the CH?
Why they're more likely to
These CH bonds we never care about. Oh, so boring. These ones we care about all the time. These ones we care about oftentimes. Now, while we're here, might as well do ethanol. H bonded to an O. I wonder if that's an acid as well. The short answer here is not in Chemistry 400. Things get more complicated in Chemistry 401. It's just generally true. All right, so now fill in the blanks. Generally, hydrogens bonded to O are acidic hydrogens. Although there are other ones too. Generally, hydrogens bonded to C are not acidic. That's the conclusion I want you to draw. I can give you more examples if you'd like. I know I haven't told that full story, but hopefully this is an introduction to that story. Any questions about this? Jeff?
Why is the last one does not count?
Oh, why? Why? Good question. So I'll give you a short answer, and then we can talk more in office hours if you want. Remember how in Chem 400 things are either soluble or not soluble? And then that's pretty true, but it gets more complicated when you consider partial solubility. That one, we consider things to be acidic or not acidic for H's, and that one's very, very slightly. So again, it gets a little, like once you peel back the layers of the chemistry onion, we say that that does get a little acidic. So I know that's not a complete answer, but that's the start of it, Jeff. And that's a good question.
You can easily mistake it for a base too.
Say that again?
Easily mistake it for a base.
You can easily mistake it for a base, and that differentiating hydroxide, sodium hydroxide, from an alcohol group, that is Chem 400 material. And so on the first exam, make sure you know this is an alcohol group and the difference between them. But I think we do. That was one of the take-home lessons from last week's discussion. How are we doing on time? Not too bad. More about H+. The H+ ions produced by the acid are so reactive they cannot exist in water. I am a hydrogen atom. How many protons do I have? 1. How many electrons do I have? 1 as an atom. Now I become H+. By losing my electron, what am I?
Proton.
I'm a proton. Hence the name diprotic or monoprotic for acids and bases. H+ ions are protons. That's it. And so they cannot exist in water because they're very highly reactive. Instead, they react with water molecules to produce complex ions, mainly hydronium ion H3O+. For example, H2O. That's an L for liquid. Sorry, it's down below there. Like so. They make hydronium H3O+. Now, is there anybody who's taking cell and molecular biology this semester? Anybody? You'll probably, how many people want to take it next semester? Because this is the darn prereq for it. Yeah, some of you. So, when you get to cell and molecular, they work almost exclusively with H+. When you get to chemistry 401, we work almost exclusively with hydronium. And this is the deeper level of understanding. But biology is complicated enough, so they use H+. There's a lot of interesting shortcuts that they in biology for chemistry things. But anyway, so there are also minor amounts of H+ with multiple water molecules, sort of like a structure like this. Let's just use H+ for now. Good. So, I think this is going to be A. Hydrogen is always covalently bonded to something. When I write HCl, and That is because hydrogen is covalently bonded to chlorine. And let me write that. H covalently bonded to chlorine. And it all comes back to this H+. H+ is too reactive, they cannot exist in water. Whenever we use H+ as a shortcut, it is almost always because H+ is covalently bonded to water, but we're going to only show it as H+ to keep things simple. So H+ is a simplification of what's true. Hydrogen is always covalently bonded to something. Jason?
What happens if H+ is made, but there's no water around? Like, will it bond to just whatever molecules in the area? Or?
That's a great question. Let me finish what I just said, and then I'll answer it. Hydrogen is always covalently bonded to something. Covalently bonded. Now, to answer your question, what if there's no water around? That was basically what you, so it's out in the atmosphere, it's in space. It's in, okay. There's one place where H+ can exist, the center of stars. But let's just assume we're not there, okay? So every place else, H+ is bonded to something, and the next thing I'll say is that in chemistry 400, there's always water around. Every single reaction we talk about, this is me waggling my head, because there's one reaction where there's no water around, and that's combustion. But even then, hydrogen is covalently bonded to something. Let me see. So it is always covalent. Like there's always something. If you bring up a situation like HCl gas, it's covalently bonded to chlorine. But you feel free to bring up places where hydrogen is, and I will tell you what it's bonded to. What's going to happen is in chapter 11, we're going to come back and do intermolecular forces. And you have to remember in chapter 11 that hydrogen is always covalently bonded to something. And the converse, hydrogen is never truly an ion. When we treat it as H+, it's because we are lazy or we want to keep things simple and we don't want to draw the whole water. So let me, that's a little bit more, is that, we're getting there. I know, that doesn't totally answer. Let me see, Alicia, what's your question?
It's part of the reason why astronomers are so interested in searching for water on other planets.
Well, so I think the main reason people are interested in finding water on other planets is because they want to find life there. If you go to, so the astronomy program at Sac City main campus, there's an astronomy telescope up on the top of Rudder South. I've gone to shows there where they have identified what's in a star and how old it is by looking for the different elements in it. And we're going to talk about that in this class and how it relates to identifying elements. But yeah, I think it's slightly different as far as finding water. Any other questions? What I love about chemistry is as you get exposed to these things, these are great questions. As you pay attention, you almost have more questions as you go, which I think is great. So But we're plowing ahead anyway. And we'll answer as many questions as we can. So, take-home message. Hydrogen is always covalently bonded to something. Remember that for chapter 11. And you should probably remember it the whole time. We've talked about this, but we're in the acid section now, so we're going to say it again. Strong acids, iodide, 100%. Weak acids, less than 5%. If you remember, I mentioned the fact that the more often you see something, the more important it is, the more likely it's going to be on your exam. I could write HCl goes to H plus Cl minus. I'm going to do it because that's just how important it is. Actually, I'm going to pick another strong acid. Does anybody have a favorite strong acid besides HCl? Nitric acid. Thank you. %. H plus and NO3 minus. H plus is a simplification, but it's a good one, and we're going to keep using it until chapter 11. Anybody have a favorite weak base that they know the formula for besides acetic acid? I do. Carbonic acid. Carbonic acid. And I'll write less than 5% right up here, even though it's already in the statement. It's my favorite one. Everybody okay with what I've just written up there? Okay. A base is a substance that yields an excess of hydroxide ions when dissolved in water. Strong bases dissociate 100%. We said the strong bases you have to know are lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, and cesium hydroxide. That's it. That's a limited subset, but that will do for us. Potassium hydroxide dissociates 100% into potassium and hydroxide ions. Coming back to my nitric acid, if I have a bottle that says 1 molar nitric acid, I do not have any 1 molar nitric acid molecules. I have 1 molar H pluses and 1 molar NO3s or minuses or nitrates. Because 1 molar nitric acid breaks down 100% into 1 molar H plus one molar nitrate. And again, on homework 3, if the question is, well, how many molar ions do you have? You have 2 molar ions. 1 plus 1 is 2. So again, this is what the bottle will say, but this is what you read. Any questions about that? In the time that we have left, we have about 5 minutes. Double replacement reactions, we've done this already. We could take whatever strong acid we want and whatever strong base. Let's use the examples that we've got over there. We've got nitric acid, aqueous, and potassium hydroxide. Double replacement says take the H plus and the hydroxide to make water. Take the potassium and the nitrate to make potassium nitrate. No matter what the strong acid or strong base, the nitrate and the potassium in this case will be spectator ions. And you end up with hydrogen ion plus hydroxide ion mixed. In the weak acid case, this should be interesting. Now we'll take carbonic acid. That is an interesting choice, by the way, but it'll still work. We will make water. What's the other product over here? Potassium carbonate. Yes. And it says salt here. I think I mentioned this. Any salt. Salt is a general term for an ionic compound that dissolves. Another salt right there. Is this balanced? No. It is not. I have two potassiums. I think I need two waters as well. Does that look right? We said that weak acids, the dominant species in solution, whole molecules, so this comes straight down. For the net ionic equation, I am going to cancel out the two potassium ions that are spectator ions. We're skipping a few steps here, but we end up with the NIE. And the NIE includes the carbonate ion because carbonic acid is the dominant species of the. How many people plan on taking Chemistry 401 next semester? Lots of you. Huge. These nationics are huge, especially with weak acids. And you will write nationics to deal with acids and bases next semester. I have 20 seconds left according to my watch, and we are done for today. Seems like a good stopping point. We'll pick up there on Wednesday.